which I will do some of it tomorrow, but in a very, very good way. And so really the challenge is how can I describe this guy? And if you look at the electron microscope pictures of this cortex, then you see very dense network of active filaments. And whoops, what did I do? Okay. You got passive crosslinks. And if I were stopping there, we would know what to do. Because that this crosslink have a finite lifetime. And Slotman, as a matter of physics, has been dealing with such systems. They call that physical gels, and you could choose your favorite theory. And the simplest will tell you that I have a relation between stress and strain of the type 1 plus tau ddt sigma alpha beta equals beta d alpha beta. And we'll just stop there and then you'll work with that. And that will tell you that, let's say, at short time, so only this ddt matters here, and here it's du dt if you want to, if u is the displacement. So basically, sorry, it's not eta, it's d. Am I right? It's at short time. No, it's at that. Right? Then at short time, only this guy or type frequency, you can pull out omega, this is negligible, and you find that you have the behavior of a solid, right? And the elastic modulus is just eta over tau. And at long time, this is negligible now, and you have the behavior of a simple liquid. And we would be happy, and we would know what to do. But it turns out that there's one more guy in the play. I think there are lots of guys. And as a physicist, I'll be outrageously simplifying.
So Jacques, your capital D by capital DT is a convective derivative? Or is
it got all of it. Yeah. I didn't.
It probably doesn't matter.
I probably, if some people want to know more, I can I have somewhere the complete formula, but you can derive some. This is supposed to have all the covariant derivatives. So it has convective plus rotational. Everything. It's something. Well, okay, you can see later. So we have one more guy in the play. And this one more guy, in fact, looks like you have tails, and you have the heads, and it's bipolar, and you maybe have, I don't know how many, these are oligomers. So I don't know exactly how many there are, but in general, a few. And these guys, so these are myosin motors. And they can grab the filaments. So let's say I have one guy like that. And it can grab the filaments and pop this guy open, for instance, and move these filaments. And so it's a challenge how you can describe that chemically. And it turns out when we started to think about that with Frank Leischer, we had this idea that if you have cross-link there, means that you have distances. If you have distances, you can write down a metric tensor. But because of this guy, this metric tensor becomes a function of time, and you try to write down the dynamical equation for the metric tensor. And we did actually some of that. But we could not get convinced that we knew what we were doing. And so we got, after some brainstorming with Jean-François Joanny and Ken Sekimoto and Carson Cruz, we got a different type of approach. And we decided to use generalized thermodynamics. And why to use generalized thermodynamics? Well, for I would say 2 reasons. One is that you know where you're starting from. So you're starting from a known state, which is thermodynamic state, and you drive it slightly out of equilibrium, but there's a well-defined procedure on how to do that, and well controlled, and it has been successful for many systems, or superfluid, liquid crystals, polymers, and so on. So it gives you a handle on how to tackle the problem. It has an obvious shortcoming, which is that biology is not close to equilibrium. In many aspects it is, but there's one aspect where it's not. It's the chemical reaction type of aspect, which is essentially ATP consumption. You know that ATP is about 10 kT, and so 10 kT is not small compared to 1. But I will achieve, and in fact the relation between speed and force, for instance in motors, is in a very wide range, almost linear, so it's not so bad. But I will discuss along the way what the limitations are. So you could use different approaches, and for instance for different systems, but for discussing swimming of bacteria, for instance, or Chlamydomonas or whatever, Sriram Ramaswamy and Aditi Sima, for instance, I've directly assumed that you can use partial differential equations for describing the dynamics, and you write down the most general form that is allowed by symmetry, and you don't care about Onsager relation because there's no reason for Onsager to be there, and bingo, and it works. The problem is that you don't know if you start from you don't know if the state exists, but you can assume it exists. And then, you don't know how, you've written the most general form. It may be, in some cases, too general, but after all, that's what theory should be. Okay, the third...
So Jacques, you'll tell us the definition of it works. In a way, it works in the sense that you can make predictions. Or...
It works in the sense that you can make predictions which are borne out by experiment.
Okay.
Yes. Yeah. That's the meaning.
And there's a proliferation of couplings, but they're not unmanageable. You don't have 40 coupling constants, or
they are not unmanageable to some extent.
To some extent.
Yes. Yeah. That depends on how. Okay. What else? So the third approach is you write down a model, a microscopic model, and you work out you get up to the point you get your macroscopic equations, and then again you have you wind up with gradient expansion, just like Sriram Ramaswamy and Aditi Sima, and it's fine. And the only problem is it's very difficult, and all you can do is low density. And you've seen it's very dense, but still it's useful, very useful. All right, so the thermodynamic approach, first you have to identify the number of conserved variables. So you want to know what are the slow variables. And the slow variables tell you that you can reach local thermodynamic equilibrium. So you have to identify conserved quantities. And there is another set of variables which can give you slow dynamics, and these are order parameters connected to the breaking of continuous symmetry. And in that case, so continuous symmetry. And in our case here, if we just look, conserved quantity, I would say actin to some extent, well, of course, myosin. I'm saying to some extent because I'm going to cheat, and I'm going to forget about myosin in the. Although we know how, in principle, we know how to include that, but I will forget about it. Then, yeah, the solvent. And of course, I mean, you would have, if I was to be exhaustive, this list would be unmanageable because you have so many other proteins. And so I had to, in fact, I had to present the spirit of that to committees at the Curie Institute. And these committees are made of 90% biologists and medical doctors. And then I would tell them I don't know what a protein is. Then I was expecting them to shoot me, but actually they did not. So I hope you don't shoot me. But we know there could be a lot more, and you'll see how sloppy we are. Now, the one which is extremely important is momentum. And interestingly, in the biophysics community, it's not always done correctly. There are a few interesting mistakes sometimes. Now, what more? Yeah, of course, broken symmetries. So now, in my drawing here, there's no obvious broken symmetry. And here I would say that there's no broken symmetry variable, for instance. But these guys are polar. So as you know, actin filaments are polar. And I can define locally a polarization vector. And quite often, in practice, the average direction of this polarization is non-zero, which means that you have a polar nematic. And so in other cases you could say, you can perturb that structure and you can get locally a nematic order, but which will not be, which will relax if you relax the constraint. And so then you are in the isotopic phase, but close to a nematic ordering transition, and then the natural order parameter, something Q alpha beta, which is B alpha B beta minus 1/3 delta alpha beta, and where I decide that P is a unit vector here as well, when I am in the nematic phase. Now, all of that, with all these low variables, you know that there is a local, you can define local free energy, so density of your conserved quantities, this polarization vector here is gradient, and so the total free energy will read the sum over the volume of 1/2 rho v squared, where v is the barycentric velocity, and if you are in 3 dimension, d3x0, or 2 dimension if you must do that as well. And now you can take the derivative of this guy, and this is a well-defined procedure, and you wind up with something like you can write the free energy derivative like again sum of the volume of minus sigma alpha beta, so the stress tensor the alpha beta, the velocity gradients. And this is this is standard calculation. I have to make sure I don't mess up the indices. So here's the symmetrical part, here's the anti-symmetrical part. So it's that piece you are used to, right? It's just dissipation due to a velocity gradient. So that's what you would have with any fluid. So that's quite standard. This piece, maybe less. I mean, those who know liquid crystals know that, but this piece is less standard. And in fact, you don't want, if you have pure rotation. So this is the vorticity piece. So V alpha beta here is 1/2 of D alpha V beta alpha. And vorticity is omega alpha beta is 1/2 D alpha V beta minus D beta. Okay, but this is background fluid rotation. So with background fluid rotation, there should be no dissipation. So that gives you a relation between this guy and this guy.
So the definition of the H's, are you going to tell us what the H's are?
Yes, I will.
Okay.
Yes, thank
We
you.
can wait.
So please ask questions.
Sorry, I'm unable to read after the H alpha, dp alpha, then the last term.
dp alpha dt, and this guy again, this is a time derivative with convection and rotation.
And the term after.
And this one I will describe as well. I will tell you what it is because this is the most important one.
Maybe you can just spell it minus R delta mu.
But
I think they can't read it. So maybe
it's minus R delta mu. I'm sorry. So this one I will tell you what it is. Okay. So this is typical of liquid crystals, and actually as a result, it tells you that there is an anisotropy part of the stress tensor, which you don't have usually in conventional sites. And it creates, and imposing that there is no dissipation with the pure rotation gives you that sigma A is right there.
Excuse me?
Excuse me,
Yeah, give it please.
could you maybe, again, because we first repeat, what are the symbols and what they mean, or can we make
Yes.
it read, or kind of identify
Yeah,
what?
so this is the stress tensor.
Yeah.
So the symmetric part of the stress tensor, this is the anti-symmetric part of the stress tensor, this is the velocity gradient, the symmetric piece, and actually I should, no, that's okay. This is the vorticity. So this is the anti-symmetric part of the velocity tensor. Now, P is the average order of actin filaments. So when there is a ordering of, when the direction of the actin filaments is on average parallel. Now I have, so I didn't speak of all of that, right? So I have to define H.
And P is a unit vector, is that right, Jacques?
P, I decided it's a unit vector,
Okay.
yes.
And the same P appears in the
So
Q alpha
here-
beta tensor as well.
But
That's a P or an N or?
Well, that's a P because.
It doesn't matter, yeah, okay, good.
Right, and this is the average, and this would define a nematic order even though it's.
Yeah.
Right, it's an index one, right? That's the alpha B beta.
What?
The alpha B beta.
Ah, that's beta. I'm sorry.
Oh, no, good.
Yeah. All right, so now H, so I have to tell you what H is here. And H is the field conjugated to P. So it's minus the functional derivative of the free energy with respect to P. And this is what in your on your liquid crystal TV or on your watch, when you switch, when the direction of, and then you get a given pixel, you switch the intensity of a given pixel, you're playing with this guy. Actually, you're acting on the liquid crystal direction exactly with this guy. And I will describe a little bit later. I'll give you some examples. Now, so I should, so it should be 1/2, I think, H beta P alpha minus H alpha P beta. You can see if you plug that in here, then this guy becomes symmetrical, and the dot product with this anti-symmetrical guys here is 0. So, but that tells you that in these problems you have an anti-symmetric part of the stress. We will not use it so much. No, here. Yeah.
And for the symmetry part, you use viscoelastic relating like you want to know.
Oh, we'll get to that.
Okay.
We'll get to that because that's the most important piece. Yes.
So there's no work done by this middle term within this linear
Yes, there's no work done by these guys here. You don't work because it's just pure rotation. Now, this guy. So this guy is the flux of a given, so species I, let's say for instance the acting flux, but you have to define it, and in fact, let's see, so one way you can define is that you say, define the velocity of, let's say, polymeric actin is well defined. It's something that you can, you can look on an image and you just sum up all the velocities with the acting mass connected to that, and you find a barycentric acting velocity, and you write it as the total barycentric velocity plus something, and this plus something you write plus a flux divided by the mass density of active polymeric actin. Then I can write the same thing if I have another, let's say, like monomeric actin, for instance. I can do the same thing. Again, I put here the barycentric velocity. That defines me another flux divided by the density of monomeric actin, and then I decide to write the solvent now as again the barycentric velocity minus the flux, this guy here plus this guy here, divided by the solvent density. Now you see that if I multiply this guy by the density of polymeric actin, this guy by the density of monomeric actin, this guy by the density of solvent, so I wind up with rho PdP, rho MVM, rho SVS equals V alpha times rho P plus rho M plus rho S, which is a total density. So I got indeed a definition of the barycentric velocity. Okay, so that's the And that's what you do conventionally with normal fluids.
So you don't distinguish between dimeric actin and trimeric actin? It's either a polymer or it's a monomer?
I could.
You could,
I could.
but it would make it very
It
complicated.
would be costly.
Okay.
Yes, yes.
All
But
right.
in principle you can.
But in practice, it's mostly very, very long polymer strands of actin with a gas of monomers that are constantly
Yeah.
absorbing and
And you'll
desorbing.
see that I will forget most of that as soon as I will give you examples. But in principle it's all there. Now, okay, so and this guy here, if you do it.
Question.
There's a question
There's
from
a
the
question.
student here.
There's a question.
Yes, please.
Yeah, I'm not understanding all the stuff on the right over there, but maybe that was what you
Here?
were about to get to. Oh, no, on the right of the DFDT.
We're coming.
Oh, you were,
So,
Which one?
I think it was the one that you were about to go to.
I'm getting to it.
Yeah.
Okay, and so and that's so that you would have with any multi-component fluid.
and there's a summation convention in that penultimate term. And there's chemical potentials there? Is that, sorry,
So
John.
yeah, so I still have to give you the chemical potential.
Thank you.
So, so I'm looking for. So mu. So mu P, for instance, is mu, the real chemical potential over rho P minus mu S. Chemical potentials are usually, they're always coming into differences, and in that case, this is the combination which is important, and it comes from that choice. I could make other choices, and then I would subtract it by something else. So, up to now, this I could have with a multi-component liquid crystal. So you can, there is an extensive literature on that. And there's nothing new there. So the only new piece is here. So it is just this guy, 2 scalar, R delta mu. And R is the ATP consumption. So let's say it's dNdt, and so we call it dNdt if N is the number density of ATP. And delta mu is the chemical potential difference between ATP and the products. So between ATP and ADP in phosphate. And this guy, for this theory to make sense, in principle, this guy should be small compared to KT. And we know it's 10 times. So that's the main caveat, but you know that you're starting from something that you control. And this is the only new thing in this theory.
So there's a term with the chemical potential. Then there's a term next to it that refers to time change in the director. And then the last term is R delta. I'm sorry, I couldn't see if there's a minus sign or if it's all one giant term.
All these, signs just depend on how you define things.
Yeah,
But there is a minus
two
sign.
separate terms.
There is a minus sign.
What?
2 separate terms. Right?
Yeah.
Good.
Good.
Yeah, okay, so now, so this guy, sorry. So this guy we defined already, and this guy is just the covariant derivative of this other parameter.
Excuse me, is that a derivative or an integral? Is that an integral with the alpha to I?
That's a J.
J.
J with a subscript alpha and
Yeah,
superscript
J.
I.
You sum all the alphas all the time because you want the scalar in the integral. Okay.
And the H
Is there
perp,
any other question?
the H perp is the local field that is perpendicular to the local director direction. Is that what H perp is?
I didn't write H perp.
But it looks like H perp on the.
It's
H
H alpha.
alpha.
I understand, but that's an H alpha also.
Yeah.
Yes.
Thank you.
I'm
Sorry, I can't see you.
Actually, that's because you know too much.
Well,
And you know, I didn't want to,
No, it's fine.
in principle, if P is 1,
Yes,
then it's necessarily H per, I mean, it depends on how you do it.
okay.
If you want to keep all three components, that you need to introduce a Lagrange multiplier,
Yeah,
like we had the other day.
thank you.
Okay. Now, then once you're here, you have to choose the what are your fluxes and what are your forces. And so the choice, you will choose the fluxes and forces. And again, here you have, there is an amount of arbitrariness. The physics at the end of it will always be the same, but you can choose whatever in fluxes and forces. And the convenient choice is to take sigma alpha beta as a flux, so the stress and the flux, and the velocity gradient as a force. The particle flux is J alpha I, and the flux is natural. You have the gradient in chemical potential as a force, so for species I. And now, as a flux, the time derivative of the, say, polar nematic order, and the force, the conjugate field, which we already defined, and the rate of ATP consumption, and the conjugate field is the chemical potential difference between ATP and the product. Okay. Now, I will just consider somehow, because it's kind of frightening to have so many components, so I'll cheat and I will start by consider just one component. So I don't have to worry about these guys, and I just have to worry about that guy, and that guy. Where is... So let's start with the first. So sigma alpha beta is, and I skip some subtleties like the Emergent tensor and so on. So those who either know more or want to know more, they can come to me and we can discuss about that privately. So the first thing is, if you want to do it carefully, you have to separate what are dissipative terms and reactive terms. And dissipative terms are those terms for which the field has a different signature than the flux. And for instance here, an obvious candidate is velocity gradient. And if I wanted to be complete, I would have to take into account the fact that this viscosity here is a force rank tensor. And so for, let's say if we are dealing with an isotropic case, I would have to split the trace part and the traceless part, and that would give us two viscosities. If we were in a true nematic phase, we would have 5 viscosities, but let me just put one. Okay. And then there is And so this is just, so we explain in terms of the forces. So I skip that guy, now I have to know what I should put with that guy. And this is liquid crystal physics. Again, you can open your book, your favorite book on liquid crystals, and it gives you something which is P alpha H beta. And you see that you need to have indices here, and this guy actually is a symmetry guy, showing up just P beta H alpha, and then it depends whether I keep the trace part or not. If I don't, so I put up some more here, and then I need to know what I do with that force. And so what can I do with that force? You will have a coefficient here, which I don't know a priori what it is. I have that force, but I need to put enough symmetries, and the one thing is P alpha P beta. And if I consider the trace piece, I will have minus 1/3 delta alpha beta. But I can also have an isotropy piece, which would be delta bar delta nu delta alpha beta. And I didn't write this writing is not perfect. I should also single out the traceless and the trace part.
So neglecting the second line, for simplicity, we are leaving out the monomers. Do we just have long polymeric actin, for example?
Forgetting about monomers.
Okay.
And if I, in fact, if it's a one in the one component description, automatically that velocity here is, and if I decide to describe the actin gel, this is the velocity of the actin gel. And I'll come back on that, because there is some subtlety here.
Question?
That's liquid crystal physics, and I'll give you examples of what it does. And that's new, that's where the new physics is, and that's where the motors come in. Yes?
Sorry, that last symbol over there, it's a delta mu, right? It's not.
No, this is,
Yeah.
thank you.
And the solvent is gone and the actin is present, or are they you're just doing solvent? What happened to the solvent?
So it's gone. I'll come back on that.
Okay.
So I'm only acting there,
Thank you.
right? And now, but we can just look for a second. I don't know, I'm not doing so well with time, but anyway, it's not so bad. Suppose I can cook up a geometry where there is no velocity. And where I keep the orientation of my guy fixed, so that I don't have to worry about this liquid crystal term. So what this term tells me is that the motor can stress the system. I can have a stress without velocity, whatever, just because of motors. I don't know the sign of this guy here, a priori. But models, and in fact, more importantly, experiment, tell you that it is negative, so this acting gel is contractile. And in fact, you can measure. So I hope I will have time to show you how you can measure that term here.
Both zeta and zeta bar are negative, or just zeta?
So we have no information on what is this guy. I mean, the relative importance of these two guys. Both of them are contractile.
Thank you.
But so I would argue that if you write down the equation for the dynamics of bacteria or algae, you wind up with similar terms, and they can have different signs. So bacterial colony are extensile; they are not contractile. So you can pretty much worry about these two signs. You can cook up and I'll show you how there is a condition in which this guy is zero. So that the stress is zero. And if the stress is zero, you see, again, I forget about that piece, you see that the motors can set up the system in motion. And it will set up shear. But this, so it means that this system has this spontaneous ability to move. And it's, and you like it because it's life, so to speak. All right, so then you have to write down dp alpha dt. And then how do I write that? Well, the first term is something that you have in liquid crystal. It's just relating linearly, again, force and flux. There's another term which is connected to that term by Onsager relation. Well, not actually, more like Schwartz relation, because if you look at this term and this term, they are reactive terms. So there is no dissipation connected to this term because they have the same time signature as the stress. And so that's why you have minus sign here. And now it reads if you P the alpha zeta. And this is liquid crystal physics. And in fact, there is for those who like old stories about how these equations have been written. They were written in a completely different logic by applied mathematicians. And then the physicists came into the game. And in fact, there was this so-called Harvard description. And they showed that what applied mathematicians believed were viscosity coefficients turned out to be completely reactive coefficients. But that's it's somehow for us it's a detail today. But there is a few years of debate about these coefficients here. And I'll show you what it corresponds to. Now, okay, now we are left. So we have this field, we are left with this field. And this field, if I am dealing with a ferroelectromatic order, I can just write some coefficient times this force of the chemical potential difference between ATP and the product. And you need a vector there, and I have a vector which is just P alpha. But this term is not so important. It's a longitudinal term. And now if we are in the ordered phase, so in the phase where I can set that to 1, either I can skip it knowing that there's nothing to be expected along the director, or if I am serious, I will use a Lagrange multiplier, but I will see that anyway it will disappear after. So this one is not so important. If we were, let's say, suppose we were in the isotopic phase, and we look at polar ordering, then the free energy would start like something like RP alpha square plus blah blah. So now in df dp, the first term would be R. It would be RP alpha. So here I would have minus RP alpha. And you see that this guy now is important, and it will change the condition. And as you know, there will be a phase transition when this guy changes sign.
It's not the same R as this one. No.
Oh, sorry. No, it's not. You're right. Also P. Okay. And this is, I'm used to phase transition. I'm sorry. Okay, so let's take R sub P. And so this R sub P now comes from here. but I have this lambda delta mu here, so this renormalizes to something which would be, I can call R tilde sub p, which would be R sub p minus lambda delta mu. Which tells me that by introducing motors in a acting assembly, I can change, and by changing this activity, I can tune the transition. Something which was not ordered can become ordered, or vice versa. I don't know. So the sign of this guy again, I don't know. And model will tell me the sign, or experiments. And experiments on microtubules, like François Denel's experiment in microtubules, suggest that it's positive. I'll tell you after, maybe at the end of this lecture, or very slow, why I'm not so much using this kind of theory for microtubules. But suppose I do. What François has shown is that you can start with something which is completely isotropic, and with inactivated motors, you activate the motors and it orders.
So there'll be an experimental signature of actual macroscopic ferroelectric ordering.
Yes.
Aligned with the long axis of the cell, or how?
Oh, these are in vitro experiments, and what you see,
Yes.
see an aster forming.
I see.
You see an hour language of declination.
Okay, so it would be a giant aster, and then locally there would be radial
Yes.
ferroelectric order.
Right.
Okay, thank you.
And it turns out that in some cases this aster moves and rotates, and it's included in that do the equations.
Thank you.
Okay, where am I now? Okay, so this is, all of that is liquid crystal physics. And this, if I'm sitting in a regime with this RP is largely negative, and I can choose then, I can decide to choose a P equal to 1, I can forget about that now. Okay, now let me just describe that term because we will need it. So now let's consider a situation where we have a convergent flow in this direction, and let's do it in 2 dimensions. And that will correspond to what we will have, in fact. So so the flow is convergent in this direction, divergent in this direction. It's called pure shear, right? And let's consider, so the average duration of our actin filaments, it is just P alpha here, I call this angle alpha. And therefore I can rewrite all these equations in terms of this angle alpha. And I'm looking at a case where there's no gradient in the orientation. So I'm just looking at just this term and that term. Forget about the other one. And I can just show that then it looks like d alpha dt is minus nu1 sine 2 alpha dx vx. So the physics of that term, it shows that, so if I have, at some point of pure shear, or you can look at the steady state here. That's when this guy is 0. So alpha is either 0 or pi. And depending on the sign, and if nu1 is positive, so these are the 2 possible steady states. Now if nu1 is negative, then on the contrary, you want alpha to be pyramidal. So either, if I pull with the flow in this direction, I can align filaments in this direction. And they don't care about polarity. And now, conversely, I see that if I push, I put the filaments perpendicular to the push.
So Jacques, in your equation, you have d by dx of vx, and in your flow, the x direction is horizontal.
Yeah, sorry.
So what is the?
Yes. Thank you. X is that direction. Yes.
Okay, and then there's no derivatives with respect to Vy that come in for the precession of the angle?
Oh, because, okay, this it is pure shear.
Thank you.
dy, dx, dx is also minus dy, dy.
Okay, thank you.
So I've used that.
So it's incompressible, and okay, you've used this relationship. All right.
So what it does, and it's pretty obvious. I mean, if you pull, it will align the filaments parallel to the pull. But if I push, it will align perpendicular.
And the sign of nu 1, there's no ambiguity there. That's always positive?
No, the new one could be
Could be negative.
anything. New one could be negative. And in fact, so in liquid crystal, we don't know how to cook up such a geometry. But we know how to do pure shear.
Yes.
And with pure shear, I would do a little more work. I would have to keep the rotational piece, which is hidden here. And if we do that, we know that there is a preferred angle depending on how nu1 compares to 1. So there could be, and if nu1 is larger than 1, no, is smaller than 1, then you are in trouble. There is no preferred angle and it keeps on rotating.
Yes.
And that physics could be also as well in biological system, although I haven't seen any case where it could be, but a priori it could exist.
But the way the theory is set up now, it's impossible to have a steady state fixed angle that's not pi over 2 or some simple...
No, with a pure shear.
With the pure shear, right.
If I keep the rotational piece which is here, I can have anything. But just, I'm using that because in the examples we will have pure shear.
Thank you.
So it's just being lazy, in a sense. Okay, well, I'm very slow. Okay, I still give you some, example of how that can work. Consider it's current situation with the substrate here and the free surface here. And I will assume that the surface tension is high enough that this free surface is unperturbed, irrelevant of whatever can happen in the ball. And I start from a situation where I have this polarization like that. And I look at the stability with respect to tilt, and that tilt may be a function of the space in this direction, with Z. But I will look for homogeneous deformation in this direction, which I call X. So that T is all the equations T dx is 0. Now you see that, and I'll be essentially concerned with the off-diagonal components of the stress, so sigma x mid, and the mechanical equilibrium tells me that dx sigma xx and dz sigma xz have to be 0, but this guy told you I'm looking for homogeneous deformation, so this guy is 0, so that tells me that sigma xz is a constant function good. And, but at the upper surface here, it has to be 0. It's a free surface. So sigma xz is 0. So I told you that I could imagine experimental situation where the stress was 0, and that's the case. Now I can come back to the equations. So sigma xz is 2 eta b xz plus, so the contractility term, the delta mu, sine 2 alpha, if I put now the, I write it in the function of this angle here, and in fact there's another term which I could, corresponding to nu 1, k b2 alpha dz squared, but this is not so important. And I have the equation for the pneumatic director is d alpha dt, which is k over, okay, gamma 1, d2 alpha dz squared, plus 1 plus nu 1, bzx. This 1 here comes from the vorticity piece, but it's not. But you see that I can eliminate, so, and I'm looking for steady state, so I can set that to 0. Now I can, and this we just showed is 0. So I can eliminate the shear from this equation and put it back in this equation. No, I'm sorry, I'm not looking at this. Let's keep this guy. So I can eliminate this guy from that equation and plug it back in that equation. And I wind up with something which is d alpha dt, which is k over gamma 1, gamma 1 tilde, because I get some contribution from that. But it doesn't, but it still looks the same, d2 theta d squared. And now minus theta delta mu, some, this 1 plus u1 sine 2 alpha. And for those who know liquid crystals, of course I don't know how many of you know liquid crystal, a few, good. You would have exactly that equation if you were here applying a magnetic field. So if I was applying a magnetic field, in fact in the z direction here, so if I was applying a magnetic field here, I would get exactly that equation with here with something which would be at the magnetic anisotropy and h squared sine 2 alpha. So basically this is what you have in your computer or in your watches, not with a magnetic field but with an electric field. And you know the result. I mean, you know that beyond the critical threshold, this guy will tilt. But so here you have no field. And so how can you see that this guy is stabilizing? If I just look, so close to threshold, you know that the angle is like epsilon sine pi z over d. So this guy will contribute to something stabilizing. And now if this guy is negative, which corresponds to contractile behavior. Now this guy contributes to something, and for small epsilon, you cannot forget about sign. And so this guy contributes to a positive d alpha dt, so it tends to increase the deformation. And so when these two guys are comparable, you get a threshold. And which tells you that k over gamma 1 pi square over b square, that threshold is of the order of delta mu critical. Well, we don't care so much about this 1 plus mu 1. And there's many factors of 2, but I don't care about these factors. And you see that for large, for thick enough slabs, no matter how small this guy is, you will always be unstable. And this is a characteristic of these systems. At long enough wavelengths or large enough scale, they are always unstable.
In this case, unstable to rotations, or?
So in that case, it's unstable with respect to this guy tilting and this guy moving. Because the minute you have a tilt there, you can look at this equation and you see that there, this is a source of shear. So the minute I have an angle here, I have motion. And I would love to see in vitro experiments on that, but experiments have not been able to check this prediction yet.
But in those in vitro experiments, delta mu would have to represent some buffered concentration of ATP.
Yeah, so that you can do.
Right.
And the other thing you could do is just change temperature. You know that myosin speed, for instance, can changes by a factor 100 between 5 degrees C and 35 degrees C. So you could change activity just by changing temperature, for instance. But these experiments are not easy. And you have zillion of other instability. I just described that one because it's easy, and we've done it. But there are many other instabilities. I've assumed that this guy is 0, but if you get to large enough length scale, it's not. Furthermore, if you couple the density, you get vortex instability, you get moving stripes. There are a lot of things. But the main message is that this guy are always unstable at long wavelength.
There's a theta which should be enough.
What?
You wrote theta on the.
Where, what?
Here, instead of
Two
theta,
roots of alpha with respect to z, presumably.
instead of theta, you should have alpha.
Oh! Yes. Then you have to correct me.
So, stop
We
here.
should stop.
What?
We should stop here.
Okay, let's stop here. So I know about half, but that's what I will do. But that's okay.
Thank you.
So already a lot of questions, so maybe we just go directly to